Hello everyone, I'm Ayman E El-Refai and we're presenting to you our project Pervasive Sonar-based Smartphones Control Suite with my colleagues Ahmed Ibrahim, Mohamed Ibrahim, Mariam and Sara. This project is supervised by Engineer Hesham Eraqi and Dr. Mohamed Moustafa. Here is our agenda. We will discuss our progress since the proposal, then the Sonar implementation, pattern and gesture recognition, the empowerment outcomes, and lastly the challenges. First, our progress since the proposal. This is our plan from the proposal. We have successfully completed the first phase of our project, which includes the Sonar implementation and analysis. And in this presentation, we will cover the main aspects of this phase. This is our system architecture. We have completed the first two modules concerning the CNN models, which will help us facilitate into our next phase.
As described earlier in our project description, we plan on implementing a solution represented in Development Suite or API that uses a phone's microphone and speaker as an active sonar sensor. These sonar waves will allow users to control their smartphones using gestures or drawing without touching the smartphone screen. We found that smartphone speakers and microphones are not fully utilized, so we thought we would use the existing hardware in smartphones to create a sonar-like projection to detect the user's hand gestures to mimic certain actions on the smartphone. Next, we will be talking about sonar implementation. First part of sonar implementation is signal generation. Understanding the waveform generated is crucial as it determines the characteristics of the signal. Our waveform of choice was the continuous wave. The sensors used was a microphone and two speakers. Our signal frequency was at 19 kHz and the experimented devices was the Samsung S10e. Shown here on the right, we can see different waveforms that could be generated. The three at the bottom, FMCW, OFDM, and ZC, all rely on multiple frequencies rather than one frequency. We will discuss in the next slide why that is unfavorable to us. ZC specifically, while it is perfect for synchronization, doesn't support the Doppler effect, which is the frequency characteristics of our choice, so we were unable to use it. As for the chirp and ZC, we were unable to find adequate amount of literature supporting its use, so we were quite unsure of its practical use as well as its implementation, and therefore we decided not to use them. That left us with the continuous wave, FMCW, and OFDM, and in the next slide we will be discussing the pros and cons of the continuous wave as opposed to these other two. Slide, we will be discussing the pros and cons of the continuous wave signal. The first pro is that the continuous wave signal enables simple signal processing and low power consumption. Since the continuous wave is a single frequency ultrasonic signal which enables simple signal processing and low power consumption compared to the OFDM, which is used as the carrier to conduct object detection, which requires complicated modulation and demodulation signal processing modules. Since the OFDM and the FMCW both use multiple frequencies, the complexity in signal generation and signal processing leads to large power consumption, which is not suitable for power-limited mobile devices such as smartphones. The second pro is that the long continuous wave signal is generally used to improve signal-to-noise ratio, since the transmission energy is quite low since it is a low power consumption when it comes to signal generation and signal processing. We find that the lower the transmission energy is, the signal-to-noise ratio will also be reduced. The third pro is that the continuous wave is a system which can continuously transmit a high-frequency signal through the air and process it at the same device in the meantime. This means we have a low power consumption and simple signal processing, which means we can achieve quicker results in real time. Next, we will move on to the cons. The first con is that the continuous wave signal is more susceptible to the interference of background movements than the OFDM approach, and that it has poor spatial resolution compared to OFDM. This means that it is actually quite poor at being able to distinguish two closely spaced noise sources. However, we did test our continuous wave sonar implementation in a noisy environment, and we are fine with having it not perform its best at highly noisy environments.
After receiving the signal from the microphone, we use the Doppler effect to realize human behavior recognition. With our application, we are mainly going to be looking for shifts in frequency time domain to understand the changes. According to Doppler effect, different frequencies are generated from different motions. As shown in the figure, as the hand moves away from the microphone, it causes a frequency shift, and the microphone will receive lower frequency sound signal, and the opposite will happen if the hand moves towards the microphone. So we plan to measure the frequency shift so we can realize the hand posture recognition. Moving to pre-processing, to improve recognition accuracy, we often need to process the raw signal because we cannot use the original signal due to the much noise. So we decided to take two effective processing methods, which are fast Fourier transform and denoising, which are working well with Doppler effect. For the fast Fourier transform, the received signal represents the time domain sound signal data. Yet, since the time frequency diagram contains more useful information, we can conduct fast Fourier transform to convert the time domain data into frequency domain data. Then we can analyze the signal characteristics and eliminate the noise. Then for the denoising, environmental noise may occur at high frequency or low frequency, and the ambient noise in the received signal can change signal waveform and decrease the quality of data. However, the noise can be removed using filters which can be used to improve computational efficiency when sampling. So we can remove the environmental noise with bandpass filter.
We first start by generating a sound signal composed of a sample rate of 44.1 kHz and a frequency range of 18 to 22 kHz. This sample rate and frequency range are adjusted according to Nyquist theorem, such that the sample rate is double the generated frequency to achieve oversampling, which improves the signal-noise ratio and avoids aliasing. This takes us to the implementation of the sinusoidal wave through the formula amplitude times sine times angle in each byte. The angle is represented by 2 pi the frequency divided by the sample rate. This produces a sine wave as a PCM, pulse code modulation, file, which is outputted by the speaker of the smartphone. To record the signal, we ran the speaker and the microphone on two separate threads to ensure that both work simultaneously. The sound wave is reflected by the hand gesture and is inputted to the microphone. The application inputs the recorded audio stream into a byte buffer. Then we have to convert the recorded byte buffer into a .wav file format, which is used for the audio. Then we will be able to apply an STFT and filters to display the waveform. As discussed previously in the architecture, we save the audio from the smartphone speaker in a raw form, which is then inputted into a byte buffer. Then we convert it to a .wav format. To be able to do so, we followed this WAV file format, which is of size 44 bytes long, where we store the file specifications, such as the sample rate, sample size, the bit size of the file, as well as its overall length. We also had to adjust the indianity of the raw data inputted into the microphone to adhere to such WAV file format specifications. In the next slide, we'll show how we displayed the .wav file format. After adjusting the buffer for the WAV format, we exported the WAV file to a PC to display the waveform as shown. This waveform would later be used for analysis of the incoming sound waves.
Using the same sound file, we applied STFT to display a spectrogram showing the generated frequencies. On the left is the application generating a frequency of 19 kHz, and on the right is a zoomed-in picture which focuses on the frequencies from 18.5 to 19.5 kHz. We applied some gestures and we observed some changes in the frequency known as the Doppler effect, and this will be shown further in our prototype. Next, we will show you a demo of our prototype. In this demo, we were demonstrating a swiping left gesture. On the right is a video showing the gesture performed, and on the left is a zoomed in picture of the spectrogram. As you can see, whenever we perform the gesture, the frequency changes, and you can see it as a small spike on the video on the left. This experiment was conducted in a noise-free environment. And similarly, in the next slide we will show you the same procedure, but there will be a song playing in the background. This demo shows the procedure we're following to collect our data. In the example shown, we use the swipe left gesture, one of the main gestures we will support, and we are trying different gestures in noisy and non-noisy environments, where each gesture is labeled according to its characteristics. In the noisy environment scenario, we played a song using a laptop in the background while recording the gesture. Each gesture recorded would last 3 seconds, and for each gesture we will record 100 trials.
And now we will discuss the pattern and gesture recognition. Regarding the machine learning models we decided to use, we considered multiple models. First, an SVM that finds a boundary that creates the biggest margin between two data. It can process complex data effectively using kernel, and is used in similar products such as Finger.io. Second option was DT and RF. A DT is an estimation method for associating the observed value and the target value of a specific item. It will analyze the data and show the pattern existing between these values as a combination of predictable rules. And complex version of that would be a random decision force that will randomly learns from multiple DTs. It creates a number of decision trees and determines the results by the majority vote. One more option is CNN, which has two approaches, either using the raw data as numerical values or using STFTs and importing the spectrogram as an image input for the model. And according to the literature, using STFTs is responsible for producing much better results. After investigation, we found a paper that uses all the models with each other and comparing the accuracy results between them. We can see that CNN has much better accuracy results than the other models, so we decided to use CNN for our project. Also, we found a comparison between using CNN with raw data and STFT. We know for a fact that CNN works with images better, and that was a validation and confirmation for our point. So we chose to use CNN with STFT for our model, and that was the final decision. Regarding the project environment outcome, we will export an API as a product with a subscription model, business model. Our customers or organization will have to periodically give us payment every year, and we will deliver the product along with constant updates. We also discussed the possibility of publishing a paper out of our regarding the marketing plan. Our target audience will be NDVR game developers who are looking for new experiences for their customers. Also, app developers for special need apps for people who can't use their touch phone properly. Also, we will try to make collaboration with NGOs or other organizations that delivers sheep technology, sheep VR technology for people in need in Africa or anywhere around the world. Our marketing method, we will use social media to approach the developers and the, the tech enthusiasts. Regarding the collaborations with other organizations, we will be using one-on-one proposal marketing approach.
In addition, we have three main challenges. First, the interaction must be near the microphone. Second, limited gestures and interactions. Third, achieving real-time performance. Then, for our constraints, any distribution to the speaker can cause disturbance to the emitted sound. Also, noisy environment can affect the accuracy. For example, coffee machines with high pitch noisy can damage the signals. Finally, we must turn off other sound from the smartphone or use headphones as it can disrupt the sonar waves.
As per the discussed methods, our next approach will be to implement the CNN models and echo profiler matrix for the SVM model. Regarding the CNN models, we will have three different CNN models according to the mode to facilitate different aspects and recognition in the suite. The CNN models will cover the VR mode, gesture recognition, and controller mode. Moreover, regarding the drawer mode, it is advised by the literature to have an OFDM wave rather than a continuous wave to be able to track fingers more accurately. We will, we will be experimenting with the continuous wave, and according to the results, we will see if we need to implement an OFDM wave for this mode. Accordingly, this mode would follow the echo matrixing profiling and a SVM model. Then we will follow with the models training and validation. At the end of our project, we will be creating our product and going through the testing phase for our final presentation.
Thank you for listening, and now we open for your questions.